Hi student and audience, this is the second lecture about this topic, and the lecture title is Flyback Converter. So in this lecture we will be discussing the operation and the steady state waveforms of Flyback Converter, and this is the simplified circuit diagram of offline Flyback Converter with Optocoupler isolated current mode control. Okay. So this is our product, will be product. Actually this converter is commercialized, and it is applied to the 42-inch TV set in LG Electronics. Actually this material is taken from the workshop I presented to LG Electronics and the Samsung Electronics a long time ago, and I revised the content of that lecture slide, okay, and I modified and I reinforced something, okay. So this is the more complete story about that. So everybody knows about the current mode control, okay. So current mode control applied to the non-isolated standard PWM converters, buck boost or buck boost converters are not extremely. So I covered that many times. So you have the knowledge, okay, some basic knowledge. But this is different. This is adapted to the isolated converter with optocoupler, isolated feedback structure. Okay. So there are two main issues. First one is you need to understand some bias circuit, okay? PWM waveforms and the bias circuit of this structure. And also you need to understand the voltage feedback circuit and its transfer function, okay? Maybe that will be new for some of you, okay? And this structure is very standard. This is a very popular structure, and usually they are using this. And this PWM is NCP1230, is developed one guy from the Infineon. His name is Christopher Basso. Okay, actually he was actively involved and designing this and promoting this IC. So that IC was very successful in the past, and LG developed this converter, this flyback converter, and they applied thousand of the TV in the past. Okay, maybe now they are using something else, but in the past this is very popular and famous converter. Okay, so I'd like to address these two issues. Okay, this is something new. It is not present in the previous lectures. Okay, this so can be considered new. Okay, and I provide one additional extra page covering that. So this is the first one, and this is about the PWM waveforms and the bias circuit. Okay, so this is the power stage. We'll be discussing this later. So first, let me discuss this part. Okay, later on I'll explain every details about this, but I'd like to give you some information about this in advance because understanding this is very important. Okay, and the first thing you should analyze is this PWM waveforms. This is a current mode control. So current mode control senses this switch current through this CSN current sensing network, and the output is VI, and that is mixed with V lamp signal. So that waveform is shown here. This is V lamp signal, and this red curve is this signal. The switch current is sensed by the current sensing network. So VI is IQ. IQ is switch current times some gain is here. That is this red curve, and this is mixed here, and you are adding this and this, and then the result is this green curve. So this is the final voltage seen at this negative terminal, inverting terminal of PWM block. Okay, and the PWM principle of PWM is this control knob is fixed in finite value. Maybe there is some ripple component, but we assume the ripple component is negligible, but there is a constant here, some value, but this value should be here. Okay, that means when this and this they touch each other, they intersect each other, then switch is turned off, and this is the TS, and this period is DTS. Okay, so there is a required D to regulate our voltage at the desired value. Okay, that is achieved by the feedback circuit. So this D is fixed. Then this and this and this is fixed, and this is fixed. So V con is the first variable you can calculate. Okay, so V con, control voltage is fixed. Okay, then IX is flowing through this, and it cannot go there. This is operational amplifier plus something. So current is going down, and this voltage V con it should be same as IX times R2. So this voltage IX times R2. So then this current, this voltage is IX is passing through this, and this VCE is IX times R1 and R2. These two resistances are fixed. Then this VCE is fixed. Okay, you first calculate this and calculate this. Okay, you know this value. Then this is the fixed, and this is the fixed. Okay, by infineon. I see. Then this IB is calculated this voltage minus this voltage divided by RB. This RB, then that is IB, and IT, transistor current, is IB minus IX. Okay, this is extremely simple algebra. Okay, then IT is fixed. IT is IB minus IX, and VCE is this one. Is this one. Okay, because IX is known, so VCE is fixed. And IT is fixed, and current transfer ratio between this is CTR, then ID is CTR. Okay, so first this is determined, then this is determined, then IT is decided, then this ID comes last. Okay, student they think they should calculate this first. That is not true. Okay, this is the result of this. So in some sense, input to this is IT. Okay, physically the source is this one. This diode current is exciting this phototransistor, and IT is generated. But in terms of the circuit analysis and to understand the PWM process, the direction is reversed. So this is determined in this manner. So this value is not related to this, regardless of this value. ID is determined by this. Okay? And ID is going through this, not this, because there is a integrator structure. That means DC impedance, DC reactance is infinity. So DC current cannot go here. So then ID is entirely entering this, and this value should be much larger than 1 milliamp for the proper operation of this transconductance operational amplifier TL431. Okay, so this is the way of analyzing or designing this bias circuit. Okay, this is one thing. All right. So in the non-isolated converter, so you don't have this. Okay, this is something extra, but not difficult. But you should understand. You determine this first. Okay, based on the required duty ratio and this waveforms, current mode control and the PWM waveforms, and the desired value of this D is fixed. Then this can be easily calculated. So this the first issue is resolved here, and the second issue is this one. this one. This part is involved with voltage feedback compensation. Actually, for this case, this is one resistor, simple resistor here, one resistor, and this is the capacitor. Okay, so this capacitor and the combination of these things, all of these things, this resistive parameter, they are constant, and the CTR is constant. That determines the integrator gain. So combination of this is providing this term, okay, and the combination of this and this generate 1, 0. Okay. In the previous lecture, I told you the integrator structure is generate this combination. That is not true. Okay, I did something wrong. Okay, so I'm fixing that. All right. So integrator structure is this. So later on, you will do simple circuit analysis, very simple, and this create 1, 0, and there is a C. This is the parasitic capacitance involved with this phototransistor CJ. Okay, and this is combined with this resistor, this resistor. Then there is a one pole here, so it creates one pole here, 1G here, and this is the integrator. In this green part is generating integrator, and there is a negative sign here. So this is the expression for the voltage feedback compensation. This is the famous 2-pole 1-0 compensation. Don't call it type 2 or type something. Okay, 2-pole 1-0 compensation. Okay, if you add one branch here, so if you add one resistor and one capacitor in parallel with this, then you will create additional pole and 0, a pair of pole and 0, and combination of this and this will generate 1, 0, second 0, and the combination of these 3 components will generate the second pole. Okay, so in that case, you have 3 poles, 1 pole in origin, and 2 poles determined this circuit parameter. Okay, and 2 zeros determined this pair and this pair. That is 3-pole 2-0 compensation. Okay, but you don't want to use 3-pole 2-0 compensation for some special case. Okay, mostly this one is okay. Okay, if you use 3-pole 2-0 compensation, then you are wasting component. Okay, maybe you can achieve almost the same thing using this structure, 2-pole 1-0 compensation, if you use color mode control. Okay, so this is the second issue. Okay, so special issues with this structure has been mentioned, and later on we'll analyze this, every details about this bias circuit. Okay, and we'll analyze this compensation circuit, voltage feedback circuit, and exact expression for this transfer function, this voltage feedback circuit structure. Okay, it's not easy. Right? So very simple algebra type circuit analysis. Then everything remains the same as the non-isolated converter case. Basic principle and the performance and the way of selecting the component value of compensation is exactly the same as non-isolated version. So there is no real distinction between optocoupler isolated compensation and the regular compensation. They are the same thing. Okay, but you should understand this, right? Okay, and let's discuss the circuit structure of flyback converter. So I'm using this diagram when I explain the structure of converter. So first, to consider this. This is SPDT switch, single pole. This is a pole, and this is through. There are 2 through. This pole is always connected either this or this one. Okay. So in this is the symbolic notation in circuit component. There is a MOSFET switch connected with a diode in this fashion for this structure. Okay, when this is the turned on, this is turned off. When this is turned off, this diode is delivering the current, inductor current. So this is the common terminal, active terminal. Active switch is located here, and this P terminal, passive switch is located here. Okay, and this the C terminal, there is always the inductor is coming after C terminal. Okay, so this current should be continuous because this current is passing through the inductor. So inductor current is abruptly disconnected. The disaster will occur. Okay, so this is the structure, and I call it three terminal cell. This one. So in the buck converter, this cell is here, right here. Okay, this is buck converter, and you know this. The output voltage is always smaller than input voltage. That is the feature of buck converter. So Vs, this one. Output is always smaller than input voltage. Okay, and this is the boost converter. You know this boost converter, output turn up, output voltage is always larger than input voltage. So that is the thing where the name of boost converter is coming from. Okay, and the buck boost converter, this output voltage is negative. Okay, this is ground level. This is a positive, then this is negative. So this VO is negative, is smaller than 0. VO is smaller than 0. Okay, let me write down this way. It's negative always. Okay. Okay. And this voltage across the inductor is VL is defined in this manner for this buck converter. So when this pole is connected to A, or this MOSFET is turned on, inductor voltage is Vs minus VO, which is always positive. Okay, and when this is connected here during on time period, this active switch is turned on, then this inductor voltage is positive. When this active switch is turned on, this inductor voltage is always positive, Vs. Okay, this here is Vs minus VO, which is positive. When switch is connected to the passive switch here, then this VL is negative of this. So VL becomes negative. And here, this passive switch is turned on, then VL is this one minus this one, but this one is always larger than this, then VL is negative. Uptime period, okay? And uptime period, VL is negative because the output of this buck boost converter is always negative. Meaning of that is during on-time period for DTS, VL is positive for all three converters, and during the off-time period, during this period, VL is negative. That means during this period, inductor current is increasing, and during off-time period, the inductor current is decreasing. Okay, that is true for this all three converters. Okay, and this is buck converter. If we rotate this terminal cell by 120 degree, you will get this, and you will get this. If you rotate once more, it come back to this. So there are only three possible configurations for the basic converters, and all the basic converters during the on-time period, inductor current is linearly increasing, and during off-time period, inductor current is linearly decreasing. Okay, so the meaning of that is this one. This one is also important. So inductor current is this structure for all three converters, and this is the zero level is here. Okay, and this is the average value of IL, inductor current, and during on-time period, inductor current is increasing, inductor current is decreasing. Okay, it's not starting from the zero. There is some average value, and it start below the average, and it go above the average, and coming back and coming up like that. Okay. So during this period this is DTS period, and this is 1 minus DTS period. Okay. So because of this power conversion is possible, right? This type of switching, this SPT is switched in this fashion. So when the active switch is connected, the extra energy is going in this inductor, and during uptime period, the extra energy is going down to the load side, okay, with some finite average value. So the switching action of STP switch provide a controlled, okay. This energy level is controlled energy transfer from the source to load, okay. And this inductor is used as the intermediate energy reservoir. Reservoir is the water tank, big water tank, okay. So this is the water tank, this is energy tank, energy decreasing. So inductor is used as energy reservoir, and it stores the extra energy and discharges the extra energy. So suppose this is the del IL variation of the inductor current, then this inductor is storing or releasing the amount of energy L times del IL, this one, del IL squared. Okay, so this is the principle of power conversion. All right. So we have this one. This one is buck boost converter. So we take buck boost converter. So then we insert the transformer in between, between input and the output, and we modify a little bit. Okay, then that becomes what? Flyback converter. So flyback converter is transformer isolate buck boost converter. Okay, operational principle is the same as the buck boost converter, but there is a transformer isolation required by the law for the safety. Okay, so we need to insert the transformer in the middle. So suppose we insert transformer here. It's the same as inserting here, okay? Because this is same node. So this is the practical transformer is inserted here. This is dot. You know what that means, okay? If the current entering in dotted terminal, then same current should come out of this dotted terminal of secondary winding. There is the definition of the dot, okay? So practical transformer is inserted here. Okay, and this practical transformer is modeled as a combination of this magnetizing inductance and ideal transformer. So this is the ideal transformer without this vertical bar. This is the ideal. This is with this vertical bar. Maybe it signifies there are some core. So this is the practical transformer, and without vertical bar, this ideal transformer. Okay, that is my notation though. Okay, somebody uses something else, but I'm using this all the time. So this becomes the ideal transformer in parallel with magnetizing inductance of transformer. And originally there was an inductor. This is the inductor coming from the original structure of buck boost converter. So we have two inductance here. They can be added. Okay, parallel combination of this can be added, and you move this switch to here. Nothing is changed. Same thing, right? And you move diode from here and to there and go through this one, the winding sign of this winding. This is not a winding. This is just a symbol. Okay, it's not an inductor, not a winding. Just mathematical symbol. You pass through this and locate this, the same thing. Okay? and polarity is plus minus. Then you flip this secondary side without changing any circuit operation. Then you obtain this. Then you obtain this, and these two inductors, this L was the inductor of buck-boost converter, and the Lm is magnetizing inductance of transformer. You combine them together and consider this as the one transformer, one inductor, and you consider this is a practical transformer, and this combination of this one is the magnetizing inductance of new transformer. That transformer is called flyback transformer. Okay, so usually you want to maximize the magnetizing inductance of the transformer, but for this case, situation is entirely different. You have desired value of this magnetizing inductance of your transformer, and the magnetizing inductance of your transformer is functioning as the normal inductor in other converter topology. Okay, so inside of this is Lm is here. Okay, then, but this value, you have some desired value. Okay, then this is the structure of flyback transformer. There is some gap between two cores. Okay, intentionally you prepared the gap between two cores. Okay, then inductance of this, the magnetizing inductance of this transformer is determined by the gap. Okay, gap and free space. Formula for that is this one. You have one gap here. You have another gap here in this structure. This is called the UU core. So UU core was here, but they are separated. Okay, intentionally gap is provided in between. So you have one gap here and another gap here. You add two gaps here. LG prime is 2 times LG. LG is the length of each gap, and use here. Then this is the cross-sectional area, and this is the turns of primary winding. This is Lm. Prime is the magnetizing current of this magnetizing inductance of this flyback transformer. Okay, and you want to control this. There is some desired value of this. Then you squeeze this one. You combine them tightly. Then this gap will be reduced, and you add something in between, some film or something. Then gap will be increased. Okay. So in this manner, you can have the controllable leakage inductance of this, right? But people, they don't calculate this. They are just experimentally determine the magnetizing inductance. Okay, they squeeze this and release this, and they measure the inductance here. That you open this side and you measure inductance here. That is the magnetizing inductance, and you control this and select the proper gap or proper clamper to get the desired Lm. Okay, Lm prime. Okay, I spent some time to draw this. It was not easy to draw this. Okay. All right. Now operation is very easy. Okay. All right. So this is the circuit diagram, rearranged circuit diagram, and this is the flyback transformer, ideal transformer, and this magnetizing inductance. This is the MOSFET switch. Okay. During on-time period, this is turn on. Then Vs is applied here. Then because of this, okay, regardless of the connection of this, the NBS will be developed by the equation of ideal transformer. Okay. Then there was a diode here. This diode is reverse biased. This voltage plus this voltage. Reverse biased twice. Okay. Severely reverse biased. This is open. Then this current is 0. Okay. So this is ideal transformer. If the current is 0, then this current should be 0 by definition of ideal transformer. So this is connected, okay, symbolically, but there is no current. Okay. So this is the virtual open. Okay, so it's not connected. It's connected in circuit diagram, but no current is passing through this. So this is open, virtual open. This is possible because this is the mathematical things. Okay, we have this. Okay, this is the ideal transformer defined mathematically by the equation. All right. Then this IM is flowing through this. Okay, VS is applied across this LM. Then the current will be increasing linearly. So current is increasing here. And actually, IM is something like this, increasing, decreasing, increasing, and this is the during on time period. Okay, so this upper one is IM, this one is IQ. Okay, this IQ. All right, and during off time period, this is on time period. Okay, let me draw this here. Okay, so this is the on-time current, IM current, and during the uptime, this switch is open, then this magnetizing current create this circuit, this freewheeling path, okay, then this current is coming in undotted terminal of this ideal transformer, then the current should come out from this undotted terminal of secondary winding. That is possible by turning on this diode. So diode is turned on by current. Okay. So if you push current in this direction, diode is turned on simply. Okay. So it's turned on, right? Then something was wrong. Okay. This should be connected. And this is capacitor, okay? Then there is some finite voltage here, VO, it is fixed voltage. That voltage is reflect this ideal transformer. Then this voltage becomes this one, VO, divide 1. And this voltage is positive, then this is a positive, then this should be positive. Then this voltage becomes plus, minus is coming here. Okay, during that period, IM is decreasing because the negative voltage is applied across the magnetizing inductance. So during this is on-time period, during off-time period, this IM is this one, this is the DTS. This part is 1 minus DTS. Of time period, then this IM is passing through continuously. Okay, during on time period this direction, off time period this direction, and eventually this will reach this, and the next operational period will goes up, go down, goes up. This is the steady state operation of flyback converter. Okay, it never start from zero. It start from the finite average value. Okay, here. Right? Okay, and based on that, and one thing, this voltage is, we already know this. This is a combination of buck and boost converter, as its name indicate. Okay, so it can be considered as the combination of the buck and boost converter. So buck is coming first, boost is coming later. There's a transformer. So this is our voltage. N times Vs is VO, right? So we will prove this, but there is a finite value VO here. Okay, and then waveforms in steady state waveforms is shown here. Okay, so this is the voltage across the magnetizing inductance of flyback transformer during on time period, off time period. This is Vs. This is minus VO divided by N because of a transformer ratio, right? So volt-second balance condition should be always satisfied. So this area and this area should be the same. And according to equation of this, and this gives the voltage gain, DC gain expression of flyback converter, which is the same as the previous one. Okay, so D is coming from buck this one. 1 divided by 1 minus D is coming from the boost, and N is coming from the transformer turns ratio. IM is average value of the magnetized inductor current. Okay, so IM is continuous during on-time current, on-time period. IM is passing through switch. Okay, so this is same as this. This is same as this. Okay, during the uptime period, this IM is circulating. Okay, here like this. Okay, and decreasing. Okay, decreasing. This one. Okay, so this then this the current. Okay, this current is deflected to here, and you have N. Then this ID current is IM divided by N. Because of this turns ratio, this ID is IM divided by N. Okay, so you have this scaled IM becomes ID. All right. So this is related with this, but not the same. It's scaled down here or scaled up. If N is 1, they should be the same. But other than 1, they can differ, right? Because of the turns ratio. So this is the equation. And average value of the IM. You evaluate average value of the IM. Okay. And we know this average value of ID. We know average value of the IM is this one. Okay. So we want to derive this. This is the result of this analysis. Okay. Assume there is IM, average value of this, and then average value of ID should be IM divided by N. Okay, this is the deflect value of this average value times 1 minus D, right? Because only during this uptime period, this current is deflect the ID. So you should have a weighting vector here. Okay. So this ID and ID is the same as this load current because ID average value of this IC is 0. IC average value of IC is always 0 for the charge balance condition on capacitor. So this is 0. Then average value of this should be this, which is load current given by this. Then you have this relationship, and this relationship is used here to evaluate this one. Okay. Okay. So here is one example. Circuit diagram. We'll be using this converter somewhere. Okay. This is very important. We are using this parameter in real converter. Okay. This isolated current mode control optocoupler thing. Okay, it's same parameter. Okay, operational condition. I assume this is the 50 kilovolts. D is 0.4. R critical. I'll determine this. I'll discuss this later. Okay, and the CCM, our voltage gain is here, and the DCM, our voltage gain is here. Okay, I'll explain the CCM and DCM and the converter analysis in DCM. Show the. Okay, you can repeat everything in detail, but I want to provide some essential information for the beginners. Okay, so all of my students will follow this at least at this moment. Okay, so this is the PC model. I provide all the PC models that will be used in topic 11. So this is the first one, PC model open loop flyback. Number 1. So this is power stage model, and everything is so obvious. And we have ESR here, and this is the functional block for the PWM. Okay, so this is something extra. This is not component of the PCM. You should configure this or something else. Okay, this one is good. Okay, so this is for the PWM signal generation. So PWM. Okay, why it becomes the PWM of duty ratio of 0.4? This is the RAM voltage. Okay, so then voltage. So this is the open loop. So ramp signal is generated here, and this is the period is 20 microsecond according to this, and the maximum value is 1, VM is 1, and this voltage, this is 0.4. This is a unit gain buffer, so 0.4 is here, 0.4, okay. Then this is TS, then this period is from this proportionality, this one should be ratio between this and this should be the same as the ratio between this and this. Okay, so then this is 0.4 TS. So D is 0.4 here. Okay, all right. And you perform simulation. Everything is provided, and then you fill the blank. Okay, and you perform simulation, and you generate this using PSIM program, and calculate this theoretically, and observe that with the PSIM simulation result, and compare them. Okay, that is the homework. You fill in blank. Okay, so fill in the blank. Okay, this is the homework, but you don't have to submit this. Okay, that's for your homework. I don't want to grade that. Okay, grading time is just wasting time for me. All right, it's so obvious, but you should confirm this. All right, to understand this, particularly if you are exposed this flyback for the first time, then that will be very good to simulate this. And to get familiar with the PSIM software, you can figure out how to plot our waveforms, and how to read the peak value, something like that. Okay, very easy. The best thing about the PSIM is it looks like it's childish, but very handy, very convenient to use. Everything is just natural. Okay. So any student can figure that out. Okay, we have 8 minutes, 10 minutes, something like that. So let me discuss the DCM operation. DCM is discontinuous conduction mode. What is discontinuous? Inductor current is discontinuous. Where is the inductor? You are not seeing the inductor. It's inside of the transformer. Magnetizing inductance of flyback transformer is IN, okay? That current is discontinuous. That means discontinuous conduction mode. And here, this current is continuous like this. That is called continuous conduction mode. Okay? Don't use continuous current mode or something like that. That is not correct. Okay? There is one name for this. Continuous conduction mode, discontinuous conduction mode. Okay, there is no term current there. All right. So this is 0. This is 0. So minimum value start from 0, and it attains the peak value and reduce to 0 like this. Okay, and average value of this is somehow related with load current. So if you increase R, load resistance R, then current should, like this, should go down to have a smaller average value. But it is impossible because this negative current is not allowed here because of the presence of diode. Diode cannot carry current in reverse direction. Okay. So what actually happening is, if you increase the R, this is the borderline between CCM and the DCM, and the CCM and the DCM. And during this time, this slope is Vs divided by Lm. And this slope is minus VO divided by Lm. Think about the structure of this converter. Okay? So if you increase R, this remains the same, right? Because Vs always remain the same, and Lm is constant. This is not changing. This on-time current is not changing, but off-time current is this one. But if your VO is increasing, if R is increased, then slope becomes steeper. So at this time, slope becomes steeper, and this is the diode current. Diode current hit 0, then diode turns off, and after that, diode remains off, and it's doing like this. Okay? Right? If you increase R further, this remains the same because the slope is always the same. This Vs is fixed, and if you further increase this, it looks like this. Okay? So this is the direction of the larger R. For this case, there is a time period where the diode current is not presenting, or magnetizing inductor current is not presenting. That is, this current becomes discontinuous. So this mode is called DCM, discontinuous conduction mode. Okay, so this is the one operational mode. Okay, so think about this. Then this is the borderline. The condition of the borderline is this is the variation of magnetizing current, and this variation, half the variation is this one, becomes exactly same as this average value. That is the critical value. That places the converter at the borderline between CCM and DCM. If we increase R further, it goes to DCM. It's shown here. Okay, that value at this point, you can calculate this, and that value is called R critical. Given by this equation, you can follow this. And if R is larger than this, if R is R critical, converter is on the borderline between CCM and DCM. If R exceeds the R critical, it goes into the DCM. Okay, that is the thing about the DCM and the DCM waveforms. So everything remains same. So this is the period, DCM period. This there is no current. This is the DCM period, and this is the uptime period. Within the uptime, the time period where this diode current is non-zero, you call it D1 TS. Okay, D1 TS. Right? These are waveforms. You easily understand this. Okay, very similar to the continuous conduction case for this. But once the converter is in DCM, this IM becomes 0. Okay, then this voltage VM is 0. Then voltage across this switch is same as this one. Okay, why this voltage is 0? Because the inductor current is 0. That is not true. Because inductor current is staying at 0. Inductor current is not moving. It stays still. That means the voltage across the inductor is 0. Okay? If inductor current is staying at some value other than 0, then inductor voltage is also 0. Okay? So this VQ is Vs, right? And the gain formula in DCM, this is the magnetizing current in DCM, all right? So during this DTS period, Vn is Vs, and during this time period, the voltage across this magnetizing inductance is minus VO divided by 1, divided by N. Then this area should be same as this area. Volt second balance condition is always valid regardless of anything operational mode. Okay, so by equating this, you have this relationship, but this is not complete because D1 is unknown in general and uncontrollable. D1 is determined by the circuit operation. Then you need another equation. That equation is this one. This one. This average value of this is, you calculate the area of this triangle and divide that by TS, period, TS. That is the average value of this. That average value should be same as load current, because output load resistor in parallel with the capacitor is supported by diode current. So average value of diode current should be load current, which is this one, and this is the equation of calculating this. Okay, this is the peak value. You know the equation of the peak value. This is Im max. Okay, it starts from 0, and this is the slope. This is the time period. This Im max. Okay, this Im max divided by n is this one, because the turns ratio, and that is decreasing. That value is decreasing. This one. This is D1 TS. This one. Then this is the area. Okay. This is a triangle, so you have 1/2 here, and this is the height, which is this one, and this is this base, this one, divided by TS. Then you equate this one, and you get this. Okay? So the basic reason going into DCM is we are assuming this out voltage is proportional to R. If you increase R, out voltage increasing. In the CCM, out voltage is determined by duty ratio and transformer turns ratio. But in DCM, R is interfering with the gain equation. So we assumed this, and that assumption is validated here, because this gain is proportional to R. If you increase R, the gain will be increased. Right? So this is end of basic steady state analysis of flyback converter. Is the same as buck boost converter, except the turns ratio. Okay, and again another homework is this one. I already calculate this. This R critical is this one. Okay, you calculate this. Everything is known. Then fill in the blank. Fill in the parentheses. You have PC model here. PC model is the same as the previous one. Just this R is increased to 6. R critical is this one. So the 6 is larger than this. So surely this converter is in DCM operation. And you fill in the blank. Okay. You can submit to me if you want. If you don't submit it. All right? But practice this. Okay. All right. Okay. That's it for today. Next week, we'll go through the start from the Optocoupler, discussions about Optocoupler. And over the weekend, I'll upload the pre-lecture slide for the next week. Right? Okay, thank you. We stop here.